Okay, so this is a this is a short discussion on optimization, which I think is one of the harder problems of the book because it involves word problems. So it's not like here's a section of the book and here's like a formula for finding a derivative. So if let's say you're taking the product, you want to find the derivative of a product. Well, if it's f times g prime plus f prime times g, and as long as you remember that formula and you take the individual, take the derivatives of f and g properly and simplify, you'll get the correct answer. And I'm not saying that that's easy because there's always lots of room for error in those kind of problems. But at least but basically there's an algorithm for it. There's certain, do here's step one, take the derivative of f. Step two, take the derivative of g. Then step three, find the product of f g prime and take the product and the product of f times g, and then find their sum. So here, there's not necessarily there are guidelines, but there's not actually kind of like that kind of like algorithm type of process here. It's just a matter of just doing a lot of word problems, getting from simply we've done this word problem, we see a similar one, and then we can then we can do it, because I do think some of these problems are really challenging. So let's just look at this first problem, right? Let's look at an example here. And so what we're going to do is optimize. So we have two numbers, x and y. We're going to call them x and y. And the sum of the first and twice the second is 100. You may have seen a problem like this in algebra. Okay, and so what we do is and their product is a maximum. So we're going to, so here is this function that we want to find the maximum of this function right here, x times y, where x is the first number and y is the second number. And I really encourage you just to write out, what x means and what y means. It makes it easy for me, the grader, to understand what it is that you're doing. And also just make sure you're not using the same variable for two different quantities. Okay, so we're trying to maximize this function, this product xy, but it's a function of two variables. We need to get it down to one variable, but we have what's called a constraint function, a relationship between x and y. X plus 2y is 100, just solve for x. And what you get here is you end up with the product is 100 minus 2y times y. So now the product is just a function of one variable, and it's 100y minus 2y squared. So this is where in algebra we could do this because the graph is an upside down parabola, like the lead coefficient, what they call the A coefficient, is -2. Yeah, so the vertex is a maximum. But we'll use calculus. Just take the derivative with respect to y. You get 100 minus 4y is 0, and just solve for y, and you get y is equal to 25. And then make sure you solve for the common error, just be, oh, y is 25, we have the answer. Make sure you find the other number too. So we know that x plus 2y is 100, so you just solve for x, you get x is 50. Also, let's just verify. So the critical point y, here's the product function is 100y minus 2y squared. We take the derivative, we get y equals 25 as a critical point. And then just use the second derivative test. Take the second derivative. We see that the second derivative of the product is -4. And yeah, so we know that by the second derivative test, that critical point y of 25 is a maximum, right? If the second derivative is negative at a critical point, that critical point is a maximum because the function's concave down. So we have these guidelines here straight out of the book. So first of all, draw a picture when possible, and always assign your variables and write them out like we did right here. X is first and y is the second number. Then definitely write out and clearly make it clear, what function you're trying to minimize or maximize. So the book calls it the objective function. I don't think that's a standard term among all books. I've used books where they call it the primary function. Step 3, yeah, so the objective functions typically has more than one variable, so we need at least one constraint equation, something that relates the two variables. So some books call that, again, the secondary equation. And then you just solve for one variable in terms of the other. That's step 4, and substitute that back into the function we're trying to minimize or maximize. And then find the critical points by taking the derivative. And maybe we even have to consider the endpoints. If we have a closed interval, remember we have to look at the endpoints as a possible minimum or maximum. Okay, so we saw one problem here. So let's look at another problem straight out of the book. I think one of the easier problems in my lab. Okay, so we have this barn and we have this three-sided fence. And the barn will be one side of the fence of this pendant area. So I drew this picture here. So the sides perpendicular to the barn are called X. The side parallel to the barn is called Y. And we want to we have 600 meters of fencing. We want to maximize the area. So what it is, so we have our variables X and Y. We want to maximize X and Y, X times Y. So again, function of two variables. So, but we have this constraint. We have 600 meters of fencing. So 2x plus y is 600. And so now we can write the area function as a function of one variable. Y is 600 minus 2x. So a times y, x times y, x times y, we can write as x times 600 minus 2x. Again, we get this parabola. The area is 600x minus 2x squared. Again, if you graph the area, you get an upside down parabola, right? Because the Lie coefficient is negative. But we're going to use, so we're not going to use algebra though. We're going to take the derivative and find the critical point. So derivative is 600 minus 4x, or x is 100. The critical point is x is 150 meters. Again, take the second derivative. Second derivative is negative 4. And that verifies that x equals 150 meters, maximizes the area function. And then make sure we find the length of the other side. Again, MyLab will, if you're actually typing it into MyLab will not mark it as correct or even let you go on, I think, until you actually enter both numbers. Okay, so when x is 150, again, we just use this constraint, 2x plus y is 600. So if x is 150, y would be 300. Yeah, so the dimensions would be 150 meters times 300 meters, and that'll maximize the area. So in part B, which I did get wrong the first time because I didn't read the problem carefully. Okay, so which is why I get a lot of problems wrong because I'm going too fast. So now we have this barn. We're trying to create these kind of 4 individual kind of pendant areas, each with area where the area is going to be fixed. Each individual one is going to be 400 meters squared. So I'm going to call the sides, and we have some amount of, what is the minimum amount of fencing required to create these 4 pendant areas, each of area 400 meters squared. Okay, so the sides perpendicular to the barn we'll call X, and the sides parallel to the barn we'll call Y. And so the amount of fencing required is, because we have five sides parallel and there's 4 sides, 5 sides perpendicular, but just 4 sides parallel. So the length that we're trying to minimize is 5x plus 4y. Again, it's a function of 2 variables, but here's our constraint function. xy is 400, or y is equal to 400 over x. So now the length function that we're trying to minimize is 5x plus 4 times 400 over x, or 5x plus 1600 over x. And now let's take the first derivative. Yeah, we get 5 minus 1600 over x squared. See, the derivatives are easy to take if we just use the formulas. Okay, so we want to find the critical point for this derivative function. So just find where the derivative is 0. So solve 5 minus 1600 over x squared is 0, or 5x squared is 1600. X squared is 320. And again, just take the square root of both sides. Okay, there's actually 2 solutions to x squared equals 320, but remember, x has to be positive because we're talking about a length. The length can't be negative. So just the geometry of the problem tells us that the domain is restricted to x greater than 0. And so the only solution for minimizing the amount of fencing is x is equal to 8 times square root of 5 meters. And again, if we took the second derivative of the length function, we get that the second derivative is 3200 over x cubed. And again, for positive x, the second derivative of the length function is positive for positive x. So the second derivative test tells us when the second derivative is positive at a critical point, that critical point is a minimum. Okay, so we have to find the other dimension now. So remember, x times y is 400. So we get y is 400 over 8 times the square root of 5. And so that's equal to 10 times the square root of 5. Right, okay, so the other dimension is 10 times the square root of 5. So the dimensions to minimize the amount of length, the amount of fence that we have to buy is 10 times the square root of 5 meters by 8 times the square root of 5 meters. So yeah, I guess when you go to Home Depot or you shop for fencing, I'm not sure where to buy fencing. Or I don't know, the fencing store. Yeah, we'll just tell whoever there, we want 10 times the square root of 5 meters of fencing. Okay, so I'm going to stop here and then I'm going to do one more problem. So I'm going to stop the recording. I'm going to make a second recording for this second part.